We have two cells of EMF 3E and E respectively. We have two resistors, each of resistance R. Initially circuit is open, there is no current anywhere, and we have marked these three nodes as 1, 2 and 3. The question is that if this node 3 is connected to node 1 for certain time delta t, and then this connection is changed and node 3 is connected to node 2 for same time delta t, and this cycle is repeated for long time, then it is found that charge on the capacitor becomes constant. That means after a long time, if we repeat that cycle, that we connect this two nodes for delta t, then again we connect these two nodes for delta t time, charge on the capacitor remains same. Then find that charge in terms of given quantity, that is C, E, and if R comes, then you use R also, but I think in final answer R will not come. So let us understand the basic concept of this question. I think after a long time, if there is no change on this charge after this cycle, then we can say that after a long time, if I connect these 2 points for a time delta t, then whatever charge comes here, the same charge will go out from here when we connect 3 and 2 for time delta t, right? If this is so, then obviously we can say after each cycle, charge on this becomes unchanged. So we are going to do that, but before that we should understand a basic result which I am going to explain here. If we are given a circuit like this, here is cell of EMF E1, the capacitor has certain charge Q and with this kind of polarity, and here is resistance R, then as per KVL we should be able to write this equation. If you are able to understand this equation, then you can understand the solution. I am explaining here. KVL says that net gain or drop of potential in the circuit should be 0. That means if we proceed in one cyclic order, suppose I am moving, say, along this, say, anti-clockwise in the sense of current, then first we are getting gain of E1, and then we are getting drop. When we move plus to minus charge, we get a drop of potential by amount Q by C. And we are further going here, and here current will be like this. Across resistance, again there is a drop of potential by amount IR. When we say IR is basically, it is not potential of any point. It is drop of potential across R when we move along the current. So I can say here potential is more than this point by amount IR, right? So gain was E1 and drop was Q by C plus IR. To equate these two, gain to drop. So we can say overall gain and drop will be 0. The same thing is writing in this form. Put gain on one side, put drops on other side, and equate them. And again, consider this circuit. Suppose we have a capacitor with this kind of polarity of charge, and there is a cell of EMF E2 like this polarity, and here if there is a current I2 like this, so we should be able to write this equation as per KVL. If you are able to understand, then you will understand the solution also. And let me again explain it. Suppose we move like this. There is a gain of potential. We are moving minus to plus. So y bound q by c. Again we are coming here and we are getting gain of amount E2. And when we move like this across R, we will get a drop because moving along the current. Current is like this. So from here to here, we are going to close the cycle. So we will get a drop. So I equated drop to the gain. Right? And these two concepts we are going to use here. Let us see the solution and try to understand it. Suppose we connect this point 3, node 3 to node 1 after long time, but for a time delta t. Then circuit will look like this, and we assuming that after long time this circuit has this capacitor has charge Q naught. So obviously potential difference will be Q naught by C, which I have marked here, and I have assumed let the left plate be positive, right be negative. It is not necessary to assume like that. You can assume positive here, negative here. It will come accordingly, and the answer sign will be changed. So in this circuit, if you apply KVL as I explained here, you can write this I1 3E, it will come out 3 minus Q naught by C by R. Try to realize it, and once you have realized it, you can assume, you can say that in delta t time, this much charge, that is this much charge will flow to the capacitor. And let us now change the connection from 3 to 2. And once I change connection from 3 to 2, circuit will look like this, right? And now I am assuming current like this. See the sense of current in here. In the first case, current is going to increase charge of capacitor. Here, current which I have assumed is going to reduce charge of capacitor because it is coming out of positive plate. That means it is carrying some positive charges from here. Now expression of this current can be written like this, Q naught by C plus E by R. It is, you can understand here, which I explained here. And in time delta t, if this connection remains for time delta t, say I2 delta t, that means this much charge will flow out of capacitor, right? Flow out of the capacitor, this much charge. So this much charge flows into the capacitor in time delta t, and this much charge flow out of capacitor in time delta t. And if after this cycle, that once connection is here, then connection is here, net charge of capacitor is to be unchanged. That means these two charges should be same. Whatever charge reaches here in time delta t, the same charge should go out from here in next time delta t. So just I have equated. Equated means you can say net difference should be 0. It's the same thing. Net gain or loss of charge is 0. So I have put here minus sign. This much is gain. This much is loss of charge. So net difference should be 0. It's the same thing, or we can equate it directly. So by doing so, you can see you will get the result as Q naught equal to C. You just simplify it, you will get this result. But getting this result can be done in another way by equivalent EMF of cells. And I am going to explain that also. First, let us recall that suppose you are given two cells of EMF E1 and say resistance in this branch is R1, which may be the internal resistance of the cells also. And we have another cell and resistance like this. Then, so this is R2. Then between these 2 points, A and B, potential difference can directly be written as E1 by R1 plus E2 by R2 upon 1 by R1 plus 1 by R2. This is very popular result. Even we call it as equivalent EMF of this combination of cells. What does it mean? We connect certain current, a certain element between these 2 points. That element will feel that as if there is a cell of this much EMF, right? So if you understand this concept and use it here there was 3E resistance R, and there was another cell of this EMF E with this polarity as shown here R, and here we have a capacitor. I am not initially connecting the capacitor. Let us see. If we take these two cells, like these two cells, so we can first find the equivalent EMF. Equivalent EMF we find equivalent EMF E equivalent between these 2 points. Let us say A and B. To 3E by R, and here polarity is different from here. You compare here, they have same polarities and similar plates are on one side. Here opposite plates are on one side. So I will put here minus E by R upon 1 by R1 plus 1 by R2. So you will see that E equivalent will come out to be simply E. It will be simply E, equivalent EMF between these 2 points, right? So this capacitor if we connect completely here, will feel that it is connected to a cell of EMF E, right? That means if we keep on connecting once here, then again here, then again here, then again here, finally this capacitor will feel that as if it is part of a circuit. It is part of a circuit where the circuit is like this, because these 2 points are being interchanged very fast. So this capacitor will feel that it is connected to here also simultaneously. If you can digest it, then you can also realize this capacitor will feel that it is connected to a cell of equivalent EMF E, and therefore final charge on this capacitor will be simply CE, right? Which we have obtained here. Otherwise, if you are not able to digest it, then this is the basic approach which I explained here, right? So this is a good problem for JEE Advanced. It may be asked.